Hi, my name is Ximing Song. I'm working with Professor Zheng Zheng, and the research of my topic is compressive sensing. I'm working with a short program over the summer. And here's the outline of this presentation. So now let's just go ahead to the introduction. And here's a classic Shannon-Nyquist sampling theorem. So it says whenever we want to digitize a signal, we have to sample twice as fast as the fastest frequency component in the signal. And here's a picture of that on the frequency domain, and it shows more duration. So whenever we sample, we actually shift this around by the sampling frequency. And if we don't sample fast enough, we get aliasing. So look at this overlapping part. That's the aliasing part, and that causes some error. So that's why we have to sample so fast. But the question is, do we always need to sample this fast? Here are some applications where this is actually redundant. And the first one is the lossy compression, and the example is JPEG. So we actually throw away a lot of useful, not necessarily useful data after we get the digitized vector. And also, there are some sparse signals that in some of the reality, some signals are intrinsically sparse, which means most of the data we actually sampled are 0. So, and also there's some compressible, which are the signals that are very well approximated by sparse signals. And here's the conventional flow of dealing with these signals. We first sample them, and then we do some compression, which means we're throwing a lot of data away. And then we store and transmit, and then we decode it back whenever we want to use it. So the key problem is that we have to sample so fast here that we are wasting a lot of power and also a lot of data here, so potentially. And the ideal goal of this project is trying to build a block that randomly samples it, and without knowing where the sparsity or where the useful data is, but we can still do a very efficient sampling, and it still works. And that's the ideal goal. And here are some key concepts of this problem. So the key problem here is to solve an underdetermined system, which means we're having more unknowns than equations. And see here, the y will be the measurement vector, which means the result of the measurement or the result of our special way of sampling. And the a will be the measurement matrix, which represents the measurement process. And x is what we want, the original signal. So from basic linear algebra, we can say that it has infinite many solutions. So we don't know exactly what x would be. But under some assumptions, we can say that the exact recovery is definitely possible. So the first thing we are assuming is that x is sparse, which I already talked in the last slides. And there are also some restrictions on A, which defines how we want to measure it. There are NSP and RIP. So the NSP is the mathematical concept. It's a null space property. It deals with the null space of the signal space, which is of more theoretical interest. And here's a restricted isometry property, which is quoted more in the literature. And it basically deals with distance of the mapping. So here are some advantages of RIP. First, it's easier to verify because we can just verify the distance of the image and the pre-image. And also, it's related to performance under noise. And once it's satisfied, it guarantees some performance and some noise resiliency. And also, the intuition is not that hard. It's just related to isometry, which means the image of the norm of the image is equal to the norm of the vector itself. And the RIP actually is very close to that. It just means it does not deviate from the original distance too much. And here are some measure metrics that's proved to satisfy these properties. And we are still yet to implement these on the real system. And here's a new sample number limit. Instead of 2n, we're actually having a constant. So this whole thing will be a constant for our system. And this is a log n, which is the bandwidth. So note that it's only a logarithmic function. So we're potentially saving a lot of data by doing this. And so here are some algorithms that are used to recover the signal. So the first one is basis pursuit proposed by Donahue. And it's L1 minimization, which is very hard to do. And also there's a greedy algorithm, which is more practical, and is also very popular as well. And the key one will be the OMP. And here's the intuition behind OMP. It just says that if X is sparse, we are only using some of them in the matrix multiplication. And so only some of the columns here actually matter. So the key idea is to, by finding the correlation, we're actually finding which columns matter and figure out exactly these values by some other iterations. And here's a hardware implementation example of the OMP. And it has two blocks. The one is the correlation part I'm talking about, which is finds the maximum correlation between the columns and the final result. And here's a least square problem block, which is once we have all the useful columns, we're actually having more equations than knowns, and then it becomes an overdetermined system. And we can use the method of least squares to solve this. And here's some future work. So the theory is some mathematicians say that this is possible, but it's still not very stable yet because it has an intrinsic probability to fail. And also, we need to design some easier to implement measurement matrix. And also at the front end, we need to design some efficient implementation of this scheme, which basically means we need to implement this measurement matrix very efficiently with some real system. And also at back end is strongly nonlinear decoding process. And we have to figure out how to do that efficiently as well. And so overall, it brings some complexity to both front end and back end. And it's very application dependent that whether or not it's beneficial. And the system level trade-off is still to be evaluated more. And now I would like to thank Professor Zhang for the kind support and mentorship over the summer. And also I would like to thank PhD student Chachang Chen for all his patient help. And also I would like to thank Mike and Jonathan and the SURE program for providing me this platform to find my research opportunities. And also I would like to thank my lab mates for all the help. And thanks. And here's my reference. Thank you.